Okay, so here we go. Last section of the semester, section 11.5, choose the best model for two variable data. It would be really best thing if you would go grab your graphing calculator if you don't have it with you. If you don't have one, that's okay. You can just kind of watch and practice in class tomorrow. Because really what we're just going to do is we're going to figure out which model best represents the data that we're given using your graphing calculator. So start out by doing the warm-up. You just kind of plug the value of 15 into these equations and find out what they equal, and then kind of read through this thing and get an answer. Okie dokie? Okay, this is kind of what I got. Hopefully it's sort of what you got as well. All I did was plug 15 where x was for each of these, and these are the numbers I came up with. Here, this is an equation that models the amount that your family spent on vacation since 1997 every year. So between 97 and 05, there's 8 years, so I plugged in 8 for x, and this is what they would spend based on this model in 2005. And 8 years later, based on that same model, this would be the cost of vacation. Well, it's kind of true as much as airplane tickets cost right now. It's kind of crazy. All right, so hopefully that went okay. Let's just review a little bit of some graphs that we've studied already, what they look like. As you know, linear graphs just kind of represent a line, linear functions on a graph. They come up as a line, and this is the general notation for a linear function. Exponential is something that kind of decreases rapidly and then slows down a little bit, or slowly starts to increase and then increases rapidly. We have exponential decay, which kind of looks like this. The graph kind of looks like, I don't know what you would call that. It starts out slow and then it decreases rapidly. And here, exponential growth climbs very quickly. So that's exponential growth. Those are kind of the graphs for an exponential function, and this is the general notation for an exponential function. And then quadratic, you can kind of remember they were U-shapes. So here's a basic quadratic function. It's a U-shape. In this section, you may see just partial pieces of a parabola. So you might just see something like that. You kind of got to recognize that it's part of a U-shaped graph. It'd be a parabola. You might see something like that. All right, so all we're going to do here is we're going to be given data, and we have to determine by a graph which function it represents, and then we have to come up with the graph, the equation, using regression on the calculator. So take a second to enter this data on your statistics. I've already done it, but I'm going to show you how you do it if you don't remember. You go to Edit, Enter, and I have all of them on here, so you probably just start out at list 1 and list 2 and enter the numbers in here. So go ahead and do that. Okay, so hopefully you have the data in here on the list. Now what we're going to do is we're going to see what it looks like on the graph so we can determine which function it was, linear, exponential, or quadratic that's being represented here. So remember, you go up to Stat Plot right here, go to second, y equals, make sure the plots are on. So if they're not, you just push enter. And what I did was I was practicing this, and then so I have some other lists in here. I need this to actually read from list 1 and list 2, so I'm going to go down and I'm going to change this to list 1. And all I do to get a different list number is, you can see they're right up here in blue above the numbers. So I do second, list 1, and list 2. So now I want to graph it, so I'm going to quit out of this, or I'm just going to do zoom. No, I don't want to do that yet, so let's quit. And then I'm going to clear that, and I'm going to go zoom stat. Remember, it's zoom 9. And there it is. Now, of these functions, this one closely probably most represents a line. If you were to draw a line through there, you would see that. It doesn't really represent exponential, or it doesn't really represent quadratic either. So let me write that down, what we did. First we put it in the stat, and then I wanted to plot it so I could recognize what kind of function it is. And then I do zoom, I can spell zoom, 9, which is zoom stat. And that helps me zoom right in on the graph or my data points. And then I kind of decided, all right, I think it's linear. So I'm going to calculate the equation. I'm going to have the calculator calculate the equation. Stat, calc. So go back to stat, calculate, and you look at your options here, and we think it's going to be linear regression, so we're going to use number 4. And I need to tell the calculator L1 and L2 because I have more than just those two lists. So I'm going to do L1, comma, L2, and then it gives me the numbers. So it says A is 0.17 and B is 0.44. So I'm going to write that down. This would be the model for that set of data. Now, there's another thing I want you to look at on here. R squared and R, these are called correlation. It's how closely the line is actually to the data. And the closer this number is to 1, the better fit that it is. So it's at 0.93, or excuse me, 0.93, which is pretty good. It's a pretty good fit right there. And, you know, I think it's a little bit lower than it may be because, remember, our data points were sort of squiggly a little bit. And we can also see how the line fits by just going into y equals and put 0.17. I'm going to put my equation right in there. And then push graph. And so I think, you know, most of the time you see an R squared value more like 0.96 or something like that. But here, these points are a little bit off, so it's a little bit lower. But it's still a pretty good fit. So I'd say that that is the model. Alrighty, let's look at another one. Okay, so you're storing leftover chili in a freezer. The table shows the chili's temperatures Y in degrees Fahrenheit after X minutes in the freezer. Well, if you think about it, hopefully the chili temperature is going to go down. Let's see if it goes in a linear fashion or exponential or quadratic, which I doubt. Use a graphing calculator to find the model for the data. So I already entered these numbers, so I'm going to go to my sort. I put them in L3 and L4. You can see right here. So go ahead and do that. Okay, now what I want to do is I want to graph them so I can kind of get an idea for sure of what kind of function it is. So go to stat plot, on. Now I need to tell it to read it from L3 and L4. You may not need to. Depends on where your data is. Okay, and then I'm going to get out of there. I'm going to push zoom, stat. Okay, so I kind of look at that. It definitely looks like exponential growth. I got this funky thing here, and what that is it's just y equals. I got to clear that out. That's from previously. And there's my graph again. So I'm going to do exponential regression for this one. Exponential equation looks like this. So I need A and B. So I'm going to have the calculator do exponential regression. So go to stat, calc. And I don't see it here, so I'm going to arrow down a little bit. There it is. Let's do 9. Oh, no. This one right here. Exponential regression. So push enter. It's 0 or 10. And then I've got to tell it to read from list 3 and 4 because that's where my lists are. And there it is. So you can see there's A and there's B. And look at my R squared. It's really close to 100. So that's pretty good. Or 1. So I'm going to write down Y equals 98 times 0.9. Let's just do 97 to the X. And there's your equation. Easy enough. It's exponential. If you look back at the graph, it's declining. It seems kind of makes sense. It probably doesn't get cold really, really fast. All right. The last one. I'm sorry, but this one's no good. I know you're not going to be happy with me. We have to do a different one. So I'll make an X and a Y column. These are your X values here. 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, and 65. And then the Y values, how do you like that for a straight line? Beautiful. 22.3, 25.5, 27.5, 29, 28.8, 30, 29.9, 30.2, 30.4, 28.8. And as I enter these data pieces, some of you may be able to see something happening here and get an idea of what this is going to look like. Let's see what we're actually working with. What this actually represents is the speed and fuel efficiency in cars. So for instance, the slower they go, the faster they go, and if they're at that optimal speed to get the most fuel efficiency. So I, of course, have already entered this data, so go ahead and do it. It's in L5 and L6 for me. So enter yours. And once you've done that, let's go ahead and graph it. So I'm going to go stat plot. I need to go to L5 and L6. And get out of there and do zoom stat. And oh, look at that. It's a quadratic function, which kind of makes sense. The slower you go, you don't get the best fuel efficiency. There's an optimal speed for the best fuel efficiency, and then if you start going faster, that fuel efficiency is going to go down. So that is kind of a quadratic function there. So now that we see it's quadratic, we're going to perform quadratic regression. We want to get the equation. And remember, the standard equation is y equals ax squared plus bx plus c. So I need a, b, and c. So I'm going to have the calculator do that. Go to stat, calculate, and I need quadratic regression. So I'm going to push 5. I need to tell it where my lists are. Oh, that's wrong. And here we go. We got A, B, and C here. And it is negative, which makes sense because remember, graph opened down. So that does make sense. Y equals negative 0.0079. You know, it kind of fluctuates if you want to do 3 or 4 decimal places for something like that. I think when you have a really small number like that, the more decimal places, the better. Plus 0.73 x, forgot the x, plus 13.76. Okay, so there's our model for this data. You can stick any value for x in here and find the y value at that point. Any speed and find the fuel efficiency. And here our r squared is 0.9618, which is pretty close. It's a pretty close model. Let me get that. All right, again, that's our correlation. How close or how well the regression line represents the data. So that is it. All righty? Yahoo!